Hey class, welcome back. Chapter 13 is titled Solutions, so that's what we're going to talk about today. First of all, a solution can be a solid, liquid, or a gas. But what is a solution? Well, first of all, it's a homogeneous mixture of two or more substances. What is included in a mixture are essentially two things. There's a solute, which is the smallest amount present, all right? So a solute, if you want to think of sodium chloride, aqueous solution, all right? The solute would be the sodium chloride, and then it is dissolved in another, which is the solvent, right? And the solvent in this situation would be water. So solvent plus solute equals solution, all right? And when we say that it's a homogeneous mixture, it means essentially that the solution phase is going to take the phase of the solvent, all right? So even though, for example, sodium chloride, aqueous solution, even though the solute is solid, the solvent is liquid water, so the solution itself is going to be liquid, okay? And again, aqueous solutions are when water is the solvent. So I'm also going to I'm definitely going to go through this slide very quickly, these slides pretty quickly, so just bear with me. If there are some things that I just kind of skip through, that's going to happen as well, because like I said, I want to make this lecture pretty short and cover just what you guys really need to know. Some of the things that are on these slides you can read for later, that's not a problem, but so just a heads up that I'm going to kind of breeze through, especially a lot of these slides that have a bunch of words on them. Okay, but here are some examples of solutions. Ocean water is a solution where salt and other solids are dissolved in water. Again, because it takes the solution itself takes the phase of the solvent. Ocean water, the solution is liquid. Blood plasma is another example. It's a solution of several solids dissolved, I guess, essentially in water, as well as some gases as well. So solutes and solvents may be solids, liquids, or gases. Some examples, again, are sugar, right? It's a solid, it's dissolved in water, and the resulting solution is a liquid, okay? That is because, again, a solution that forms has the same physical state as the solvent. Sparkling water is another example of a solution, but the difference between that and sugar water is the solute is in its gas phase, CO2, and the solvent, again, is liquid water. And here, again, the resulting solution is liquid, and CO2 is the solvent. So down in table 13, we have several examples of certain type of solutions. Let's first look at gaseous solutions. The solvent is going to be a gas, and turns out the solute is also a gas. Air is a major component. We don't need to talk about necessarily what is the solvent and what is the solute for air, but just remember that air is an example of a gaseous solution. There are also liquid solutions where basically all of the liquid solutions that we have here are all, the solvent is all liquid, but let's take a look at what the solute is for these guys. We have a gas liquid solution, again, that's sparkling water. A liquid solution such as vodka, where you have ethanol as a liquid as the solute and water as the solvent. And then again, we have a solid liquid solution where the solid is a salt, right, and other solids dissolved in water, and seawater is the example. You can also have solid solutions where you have a solid dissolved in a solid. Brass is an example of that. It's a solution of copper and zinc and other alloys. Okay, so you can have gas, liquid, liquid, solid, and solid. This is a repeat slide, so I'm just going to skip it. So again, why does a solid dissolve in water? Why does that happen? And what you need to understand is that, so for sodium chloride, for example, we've talked about this before. Sodium chloride, when we dissolve it in water, it breaks up, we know, into its respective cation, right, and anion. I'm going to put that over here. All right, so originally it's in this solid phase right here, and then when we throw it in water, what happens is that the attraction between the water and the respective ion is greater than the attraction essentially between the cation and anion in the solid form. And again, that's because the really, really interesting property of water, right, where the partial negative, I'll zoom in right here, the partial negative on the oxygen, all right, is attracted to the full-on positive charge of the sodium cation. So you have several water molecules that surround the sodium cation and essentially form this like bubble sphere around the sodium cation and keeping it essentially away from the chloride anion. On the other side of water, right, where the hydrogens, you have a slight positive charge. Again, this has everything to do because of the shape of water. We've talked about this before. Water is considered polar because there's an uneven distribution of electron density. There's more electron density around the oxygen than there is around the hydrogen. That results in these partial positive and partial negative charges. The partial positive charges on hydrogen are attracted to the chloride full-on negative charge, the chloride anion, right? And it does essentially the same thing, but flipped. It surrounds the chloride anion, forming this bubble around it and keeping it away from the sodium cation. So this is just another example. You have sodium chloride in a crystal lattice. When it's a solid, we throw it in water. The cations and anions break up, and they are evenly distributed throughout the solution. So what's going on within the situation? Why does something like sodium chloride, again, become dissolved? We already talked about it on a molecular level, but let's talk about it on a just strictly interaction level. So there are 3 types of interactions that come into play here. We have the solute-solute interactions, which are the attractive forces that hold the solid together, all right? That's the sodium chloride in solid form. That is the attraction forces that hold the sodium cation close to the chloride anion. All right. We have solvent, here, I'm going to skip this one really fast. We have solvent-solvent interactions. This is the attraction forces between, for example, water molecules. Okay, so that's this attraction force right here. The solute-solute interactions that we talked about up here are the attraction forces that keep the sodium and the chloride together. And then finally, we have the solvent-solute interactions, right? This is the attractive forces between the water molecules and the sodium chloride units. So that's these attractions right here. So in a solution, in order for something to dissolve, in order for a solid to dissolve, the solvent-solute interactions must be greater than the solvent-solvent interactions and the solute-solute interactions. They must be greater, and if they're greater, and that's a very, what do I mean by greater, right? What do I mean by favorable? And there are lots of ways for me to describe what favorable means or stronger. But in this case, in this class, what you have to understand, we don't have to go into math, or we actually don't even have time for that kind of situation right now. But let's just go ahead and just say that because there are so many water molecules, right, per ions, and because the water molecules are attracted to the ions in a respective manner, right, those attractive forces are greater than the solvent-solvent attraction or the solute-solute attraction. And if they are greater, that means that the sodium chloride units will break apart and it will dissolve in water. Okay, and that's pretty much all you need to know about that. So again, solute-solute interactions and solvent-solvent interactions have to be less than, right, weaker than the solvent-solute interactions in order for a solid to dissolve. So we know that when sodium chloride dissolves in water, it forms free-moving ions in solution, and it forms an electrolyte solution, right? Again, electrolyte solutions are solutions that contain dissolved ions, and then therefore they can conduct electricity. But what about something like sugar? All right, a sugar solution, right? Sugar dissolved in water is different than sodium chloride dissolved in water. Sugar, we call it a molecular solid. Another way to say it is it's covalent. Okay, we know that when we put sugar in water, and if you don't know this, you do now, when we put sugar in water, it does dissolve, but it does not conduct electricity. It is a non-electrolyte. It does not conduct electricity. And this is because even though sugar dissolves in water, it forms neutral particles, meaning it's not charged ions, it's neutral particles, and because it's a neutral particle, meaning particles without a charge, it does not conduct electricity. Okay, these are non-electrolyte solutions. Non-electrolyte solutions are solutions that are, the solute is a covalent compound, like sugar. And when that solid dissolves in water, it does not form free-moving ions, and therefore it does not conduct electricity. So, again, what's going on when sugar is dissolved in water? Well, here's a really basic example. All right, in solid form, each little one of these purple ovals are a sugar molecule, right? C12H22O11, C12 or C6H12O6, all different types of molecular formulas for sugar, but in the solid form, these sugar molecules are basically stacked on top of each other in this type of arrangement. They're really close together, but there's no actual bonds in between the sugar molecules. Okay, there is some solute-solute interactions, right? There is some attractive forces between the sugar molecules, but it's not a full-on bond. Okay, when we throw it in water, for example, this is it looks like a cup of tea or whatever. What happens is that the attractive forces between the water molecule or the sugar molecules, right? These are all the attractive forces. They break apart, right? So all these attractive forces break up because the attractive forces between the solvent, which is water, and the solute, which is sugar, is greater. So we start seeing these, attractive forces disappear, right? They go away. And then what happens is that the sugar molecules separate from each other. They're surrounded by water molecules, similarly to how water molecules surround the chloride anions and the sodium cations. And what they do is, like I said, they break apart these slight attractive forces, and then the sugar molecules do float freely in solution, and they are evenly distributed throughout the hot tea, assuming that it's all the same temperature. But the big take-home message is that the sugar molecule stays intact, and it stays intact as a molecular compound, a covalent compound with no charge, right? So there's no charge. And because there's no charge, it doesn't form an ion, and therefore it doesn't conduct electricity. So we're going to talk a little bit about solubility really fast. Solubility is can be measured qualitatively. All right. So I'm going to go ahead and I'm actually going to skip this slide. So solubility, all right. The solubility of a compound is defined as the amount of the compound, usually in grams, that dissolves in a certain amount of liquid. All right, so let's look at sodium chloride for an example. All right, how much sodium chloride? Can we just start throwing a bunch of salt and water and then just infinite amounts of salt in water and it will constantly dissolve? And the answer is no. There's a certain cap to the amount of salt that we can put in water. Okay. First of all, the solubility of salt is temperature dependent. All right, so the solubility of sodium chloride at 25 degrees Celsius, I'm going to change the color here, at 25 degrees Celsius is 36 grams per 100 grams of water. So that means that we can, in 100 grams of water at 25 degrees Celsius, we can throw in 36 grams of sodium chloride and be confident that all of it will dissolve. All right, this is called a saturated solution. This is called a saturated solution. And the reason why it's a saturated solution is because after 36 grams, that 100 grams of water, we can't fit any more water. We can't fit any more salt in there. There's no more room. So it's considered saturated, okay? So again, when we talk about solubility of something, sometimes we'll talk about it in terms of the way that we just described the sodium chloride, where 36 grams of sodium chloride can dissolve in 100 grams of water. Okay, after 36 grams, the solution is considered saturated. If it's under 36 grams, it's considered unsaturated. Right? So unsaturated solution is holding less than the maximum amount of solute. Right? Again, a saturated solution holds the maximum amount of solute under the solution conditions. This is also important. If additional solute is added to a saturated solution, it will not dissolve. All right? It will not dissolve. It'll just sink essentially to the bottom. If the solid is more dense than water, if it's less dense, it'll float to the top. The take-home message, it won't dissolve. A supersaturated solution is something that's not necessarily that important for this class right now, but just to be thorough with the terminology here, it is one holding more than the normal maximum amount of solute. The solute will normally precipitate out or come out of a supersaturated solution. So we work with supersaturated solutions when we're trying to purify compounds in chemistry. Okay, you'll learn more about this in Chem 200. So, again, we can talk about this really fast. When a solid is added to a solvent, which is soluble, the solute particles leave the surface of the solid and become solvated by the solvent, initially forming an unsaturated solution. So that's this example right here. I'm going to zoom in really fast. So again, you have this solid crystal lattice, right, or this a solid compound. We throw it in water, and all of a sudden we start seeing all of these solid particles start to leave the surface of the solid. Sometimes they come back, but not always. They keep going, and they will keep going out of solution or out of the solid and into solution until it reaches saturation, right? So this is a saturated example. And essentially what happens with the saturated example is that the rate at which the solid leaves the crystal lattice is equal to the rate at which it comes back down. Okay, so let me zoom out. When the maximum possible amount of solute has dissolved, the solution becomes saturated. Right, so this is a saturated solution. If the excess solute is present, if excess solute is present, so in this situation, excess solute is present, the rate at which the solute particles leave the surface of the solid equals the rate at which they return to the surface of the solid. Okay, so an example of this would be if we have, we'll say 36.5 grams of sodium chloride in 100 grams of water. All right, it's definitely a saturated solution, okay, because it's the maximum capacity, right, at 36.0 grams. And then the 0.5 grams you can think about as the excess solute. All right, and 0.5 grams of that will undergo this type of reaction where the rate at which it leaves the solid and then comes back is equal to each other. I'm not going to talk about anything on the right. I'm going to skip this. Okay, so how does solubility of solids vary with temperature? All right, and you're going to need to know this. In general, the solubility of solids in water increase with increasing temperature. Increase with increasing temperature. You can think about hummingbird food, right? When we make hummingbird food, if you've made it before, a lot of times you want to throw a lot of sugar in water, right? Because hummingbirds like it. I think it's a fourth of a cup to every cup. A fourth of a cup of sugar to every 1 cup of water. And a lot of times in order to get the sugar to dissolve, you have to heat up the water. All right, so as we increase temperature, we increase the solubility of solids. And then here's a nice little graph showing you have temperature on the x-axis and solubility of grams of solute in 100 grams of water. And as we increase temperature in every single situation, and all of these are all ionic compounds, they all increase as temperature increases. Okay, so this trend you're going to have to know. Now, solubility of gases in water is the opposite. All right, it still changes with temperature like it does with solids, but it is the opposite again. So as the solubility of gases decrease with increasing temperature. And you can think about this intuitively, or a real world example is the soda, right? Cold soda, the carbon dioxide that is dissolved in the liquid, right, is more likely to stay in solution. So you have cold soda stays carbonated for longer. If you have warm soda, the gases bubble out of solution. And you can even see here when you pour, right? I guess this is cold soda, this is warm soda, and you can see the difference of when you pour it in a cup, right? Here in the warm soda, the gases clearly are bubbling out of solution at a much faster rate. Here, it's happening less frequently, or the rate is less, and that is because it is colder. Sorry. So again, just make sure you understand gases decrease, the solubility of gases in water decrease with increasing temperature. I also need to introduce to you Henry's law. All right. Henry's law states that the higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. And that's pretty intuitive, right? If you think about pressure above a liquid pushing down on the surface of the liquid, as that pressure pushes down, I like to think of it as keeping the gas molecules in the liquid. If you have less pressure above the liquid as you do over here, there's less force pressing down, right, on the surface of the liquid, and therefore the gas molecules can pop up or leave the solution much easier. So Henry's law states that the solubility of a gas in a liquid increases with increasing pressure. So that is something you're going to need to know. This is just, again, another real world example of Henry's law. So I'll write Henry's law right here. All right, another soda can example. When you have a closed soda can, right, there's a little on top of, right above the surface of the liquid within the can is CO2 that's under pressure, okay? And then and that keeps all of the CO2 molecules, I'm going to zoom in, these are CO2 molecules right here, that keeps the CO2 molecules in, gaseous molecules in solution. But then when we open up the can, as we did over here, you release the pressure, and when you release the pressure, all of the CO2 gradually leaves the solution, okay? And that is because you release the pressure. So, quick review on solubility, what we just learned. A solution is a homogeneous mixture with two or more components. The solvent is the majority component and the solute is the minority component. Water is the solvent in aqueous solutions. Solid and liquid solutions. The solubility of solids in liquids increase with increasing temperature, and the solubility of gases in liquids decrease with increasing temperature, but increase with increasing pressure. Okay, so now we're going to talk about solution concentration, all right? And one of the ways that we can measure this is through this thing called mass percent. Here is the formula for mass percent. We have mass of the solute over mass of the solution. Remember, solution is solute and solvent, okay? So don't forget about this part right here, because a lot of people screw this up. It's mass of the solution, which is, and remember, solution is solute and solvent. Mass percent is the number of grams of a solute per 100 grams of solution. A solution with a concentration of 14% means that 14 grams of that solute can be dissolved in 100 grams of solution. Okay? But it's also clearly up here, you can tell it's a ratio. So we can use this as a conversion factor, which we'll talk about in the next slide. In order to calculate the mass percent, you're going to divide, obviously, the mass of the solute by the mass of the solution, as I have indicated up here. This is just a replay of what I just said. So again, we said that we can use mass percent in calculations. We can use it as a conversion factor between mass of the solute and mass of the solution. The key to using this as a conversion factor is understanding that mass percent can be written as a conversion factor. So for example, if we have 14% like we did on the last slide, right, of some solid, that means that it can be translated as a conversion factor where you have 14 grams of solute per 100 grams of solution. The other conversion factor that we can write is 100 grams of solution over 14 grams of product of solute. Okay. So calculate the mass percent of sodium chloride in a solution containing 15.3 grams of sodium chloride and 155 grams of water. All right, so so 15, we have 15.3 grams of solute, right? We have 155.0 grams of solvent, which is the water. So the solution is going to be the summation of the two, which would be 170.3 grams. Okay, so the mass of the solute, 15.3 grams over 170.3 grams multiplied by 100. Okay, that's going to give us, here, throw in my calculator, 15.3, 170.3 multiplied by 100, and that's going to give us 8.98%. Right? So this is the mass percent of sodium chloride in solution. So essentially that means that for every 100 grams, right, of solution, we have 8.98 grams that can be dissolved. Let's do another one. Calculate the mass percent of a solution containing 27.5 grams of ethanol and 175 milliliters of water. The density of water is 1.00 grams per milliliter. Okay, so we have, obviously, the solute, which is 27.5 grams. The solvent, now we have it, we were given it in 175 ml, and we need it in grams. We were given this, so we can convert from milliliters of solvent, essentially, to grams of solvent. So, again, 175. Now, it's a 1-to-1, but I'll just take you through it. So, for every 1 milliliter of water, we get out 1 gram of water. So, that's the density, right? Milliliters can't, oops, that is my kid. Sorry. I'm going to do this really fast. Okay, that way. That won't happen again. All right, so that is 175 grams of H2O. Okay, so solution is going to be 175 grams plus 27.5 grams. Okay. 175. I like to put this in my calculator, especially while I know it's obvious and I could totally do this in my head, but I'm thinking about 7 things at once, so I need to make sure that I get it right so I don't have to do this lecture over again. So, okay, so that is solution. All right, so the mass percent is going to be 175, right, over multiply by 100. So we're going to take 175 over, oh, I didn't mean to write 175. I'm sorry. That makes a lot more sense now. 27.5. So 27.5 divided by 202.5 multiplied by 100. So that means 13.6%. So the mass percent of a solution containing 27.5 grams of ethanol and 175 milliliters of water is 13.6%. All right, let's do another example. So water sample from the bottom of this lake that was at this creepy story that's the beginning of your chapter. If you want to read it, I think you should, is 8.5% carbon dioxide by mass. Determine how much carbon dioxide in grams is contained in 28.6 liters of the water solution. The density of the solution is 1.03 grams per milliliter. Okay. So the first thing that we're going to have to do is we're going to have to take this, and we're going to have to convert it to grams, because remember, we need, this is the solution. Okay. So we're going to have to take 28.6 liters. We're going to have to convert that to milliliters because our density is in milliliters. So for every 1 liter, that's 10 to the third milliliter. All right. Then we're going to take our density, which is grams per milliliter. So 1 milliliter over 1.03 grams. That's going to give us our grams of solution. Okay. It's going to give us grams of solution. So we have 28.6 3 over 1. And then we're going to take, 1.03 over 1. Seems like a lot of grams, but I guess that makes sense. 29458 grams solution. Let me just make sure that that's right. So we have hold on a second. Sorry, I am just making sure that I have 28.6 liters, right? Multiplied by 10 to the third. Yeah. And then multiplied again by 1.03. Yeah. So 294.58, and then really we're looking at 3 sig figs, right? So it's going to actually be 29500 grams. All right, so that's grams of solution. Okay, so a water sample from the bottom of Lake Neos contains 8.5% carbon dioxide by mass. So we need to figure out how many grams of carbon dioxide is in this amount of solution, okay? So what we're going to do is we're going to use this 8.5%. I'm going to take this, and now that we have grams of solution, we're going to start off by saying 29500 grams solution. And we're going to use 8.5% as a conversion factor. And I want you to just drag your attention to this really fast. Okay? And basically what that's saying is, remember, this is a conversion factor, and this is the equality, right? So for every 8.5 grams of CO2, or for every 100 grams of lake water, we get out 8.5 grams of CO2. So we're starting off grams of solution. This is the lake water. Okay, so we're going to use this as a conversion factor, considering this equality, and we're going to sit back and say 100 grams of solution, which is the lake water, gives us 8.5 grams of CO2. Okay, and what we're doing is we're going to use it as a conversion factor, and just make sure you see, I start off with grams of solution, that cancels, I'm left with grams of CO2, which is what I want. So I have 29500 multiplied by 8.5 over 100, close the parentheses, and we have 2507.5 grams of CO2. And just to make sure that we understand how many sig figs, we're working with 2 here, so we're going to put 2.5 times 10, 1, 2, 3 to the 3 grams of CO2. Sorry, that's real messy. And that's my final answer. Okay? I don't know where that came from. Oh, this is interesting. This is not what I want, so just go ahead and ignore this. Okay? But here's our solution map again. This is just to make sure that you see what's going on. Again, we started off with, this was the solution, 28.6 liters of solution, which is the lake water. We converted it to milliliters. Your book does a little bit differently. Again, I like to put the one with a larger unit, but your book doesn't, which is lame, but whatever. Then we use the density of lake water to convert to grams, and then we used 8.5% by mass as a conversion factor, and this is what we got out right here. Okay? So, now we're going to talk about molarity. All right? Molarity is another way of describing the concentration of solutions. It's defined as the number of moles. All right, so remember, this is when we are talking about mass percent, it's grams per gram, right? Molarity is defined as the number of moles of solute over liters of solution. So it's moles of solute over liters of solution, and that's molarity. It's described, or it can be represented as a big M, all right? And it's going to be moles per liter. So M is a unit, or M is a unit, or you can put moles over liters, okay? But just remember that the units within M are moles in the numerator and liters in the denominator. Okay, and this is also saying, this is the same thing with the mass percent situation. Note that the molarity is moles of solute per liter of solution, not per liter of solvent. To make a solution of a specific molarity, you usually put the solute in a flask and then add water to the desired volume of solution, okay? So if we want to prepare 1 molar solution of sodium, 1 molar sodium chloride solution, you're going to need to take, it's a ratio, so it all depends on whatever your ratio is that equals 1, but the easiest way to do it is to say 1 mole of sodium chloride, right? 1 mole of sodium chloride is 58.44 grams. Again, we're just taking the molar mass of sodium and the molar mass, so the molar mass of sodium plus the molar mass of Cl, and that equals the molar mass of sodium chloride, which is 58.44 grams per mole. And since we want 1 mole, right, we want 1 mole, then we're going to weigh out 58.44 grams. So you're going to throw that, this is a volumetric flask, okay, so it has only calibrated to, and this one is calibrated to a liter, to 1 liter. Yeah, I should do this. All right, and that's this line right here. This is the 1 liter mark. Okay, and so if we add 1 mole of sodium chloride in here, and then we fill this up to the 1 liter mark, right, which is right here, then we will have 1 molar solution of sodium chloride, okay? Remember, this is a molarity is a ratio, it's moles per liter. So if you wanted the same amount, or not the same amount, if you wanted to make a 1 molar solution of sodium chloride, but you only wanted to use, I'll throw this, you only wanted to use, so if you wanted to make a 1.00 molar solution of sodium chloride, but you only wanted to use 500 milliliters, right? You would have to sit back and say, okay, remember, you got to express 500 in terms of liters, first of all, because we can use this as a conversion factor as well, because this means, so I'm going to write conversion factor. So 1.00 molar solution means essentially 100 mole per 100 liter, okay? So if you wanted to make the same type of concentrated solution, but you didn't want to make it a liter, you wanted to make it 500 milliliters, you could do that. What you would do is you would sit back and say 0.500 liters, right? Because I have to express this in terms of liters. We can use our molarity as a conversion factor. And we would sit back and say, all right, so for every 1.00 liters, we get out 1.00 mole, all right? So long story, this is pretty obvious, but I'm just taking you through it. So liter cancels, and our answer is left in mole. So that means we would have to do 1.500 mole NaCl, all right? So if for every 1.00 mole NaCl we have to weigh out, what was it? 58.44 grams. 58.44 grams. We can take this 0.500 mole NaCl, convert it to grams, so 1.00, I should say just 1 mole. Sorry, 58.44 grams NaCl, right? So essentially 0.5 multiplied by 58.44, 29.22 grams. So a 29, I'm going to zoom out just a little bit. All right, so again, remember where this was a liter, right? We could make the same concentrated solution, but a smaller amount of solution. And by saying, okay, well, if we have 0.500 liters of solution and we have 29.2, oh, sorry, we don't want to say. And we weigh out 29.22 grams of sodium chloride, and we put it, here's our, so we'll say this is 0.5 liter, right? We put this in there and we fill it up, okay? That's still going to give us a 1.00 molar solution, okay? So again, this whole exercise that I just did right here was to show you that a 1 molar solution, it's a ratio, okay? That 1 molar, it's a ratio of moles and liters. So you can have several types of ratios, right? Or you can have several numbers. In this case right here, we had 1 mole of sodium chloride and 1 liter of water. But down here, we just halved the number, right? All we did was half the number of the grams of sodium chloride to give us 0.5 moles. And we also have 0.500 liters. And again, you take the ratio of that, and that's still going to be 1 molar, okay? So just remember, molarity is a ratio. So I'm going to add another slide here. I usually do these on the board when I'm in class, but that's not going to happen clearly. So, all right. All right, so we're calculating molarity. Calculate the molarity of a solution made by putting 15 grams, right? 15 grams, 15.5 grams NaCl into a beaker and adding water to make 1.5 liters of solution. All right, so we have 1.50 liters of solution. Okay. So the first thing, remember, so molarity, remember really fast, I'm going to write this in black. Remember, molarity is moles over liter. So we need to first convert this, because we know that the liter of solution is going to go right here in the denominator. We need to convert 15.5 grams of NaCl to moles. And we do that using the molar mass. And again, the molar mass is 58.44. So we have 15.5 multiplied by 1 over 58.44. and that's going to give us 0, 0 point, sorry, still waiting on my new stylus, 2, 6, 5. Okay, so that's how many moles we have of sodium chloride. So you're going to just take the ratio of those two. So 0, so the molarity of NaCl solution is going to equal 0.265 mole NaCl over the liters of solution, right, which is this guy right here, 1.50 liters. So that's going to give me 0.17, a lot of numbers in here, 8, I'm going to 1 m, and then we're working with 3 sig figs, so that's stopping here. So that means because we're dropping the 8 and the 1, we have to round up, so it's going to be 0.177 molar. Okay? And oops, here you go. That's on the slide, so you can just take a look at that if you need to. I just worked it out for you, but this is everything that you need to know. So again, we're calculating molarity in this example. Okay, let's do another one. Determine how many grams of sucrose are contained in 1.72 liters of a 175 molar sucrose solution. All right, and I gave you the molar mass of sucrose. All right, so there's 2 take-home messages here. You were given liters, right? And you were given, remember, this is a conversion factor. Okay? Never start off with a conversion factor. Always start off with the 1 unit number. This is essentially a 2 unit number if you think about it. It's moles per liter, right? So we were given, and the first thing you also need to do is make sure that the number that you were originally given, the first one, that it has the right units. If it doesn't, you need to convert to the correct units in order to use your right conversion factor. Liters is the correct unit, so I'm going to say, I'll make it a little bit, 1.72 liters. Give me a second, sorry. 1.72 liters, and we're going to use molarity as a conversion factor, okay, where it says 0.758 moles per liter. One liter of solution. Okay. And then when I plug this in my calculator, I just want you to see it. So we're going to take 1.72 and we're essentially going to multiply it by 0.758, and that's going to give us 1.3, whoopsies, 1.3, working with 3 sig figs here, so it's going to be 1.30 mole, and this is mole essentially C12H22O11, mole sucrose. Now, we would need to know how many grams of sucrose are in this. So what you're going to have to do is you're going to have to take this number right here. All right, I rounded it to give you, just to show you, right, I rounded this, but my calculator gave me 1.30376. Okay, so I'm going to keep that number, but I'm just going to make sure that you understand we're stopping here because we need 3 sig figs. So again, this is mole sucrose, or I should say mole, I'll just do C12H2211, oops, O11. All right, and then what we're going to do is we're going to use the molar mass of sucrose just to convert to grams. All right, we're mole here, so mole needs to be down here. So for every 1 mole of sucrose, we have 342.34 grams. And actually, I'm just going to okay, so 342.34, close parentheses. That's going to give us 446.3291 grams. And we're working with sig figs here, so we have 3, right? So since we're dropping this, 446 grams sucrose. Final answer. Okay, so again, this situation right here, we had to determine grams of solute, right? We were given volume of solution, and we were given the concentration of the solution. So, and remember, the concentration of the solution, molarity, is a conversion factor. So we started off our calculation with the volume of our solution in correct units, okay, which is liters. We arranged our conversion factor in a way where the liters canceled, giving us moles, which is what we wanted, okay? And then we took the moles, so that's how many moles are present in 1 liter of a 758 molar solution of sucrose. Then we took 0.13 moles and we converted it to grams using the molar mass of sucrose. And then again, 446, and this is the whole thing right here. So ion concentrations is another really important thing that you guys are going to have to know. Ion concentrations, remember, because when we throw ions in solution, they break up. Okay, so the reported concentration of a solution containing molecular compounds usually reflects the concentration of the solute as it actually exists in solution. A 1 molar glucose solution contains 1 mole of glucose per liter of solution, as you know. But the ionic compounds, when we report ionic compounds, it's different. And it's very intuitive, so just bear with me. It reflects the concentration of the solute before it is dissolved in solution. So a 1 molar calcium chloride solution contains 1 mole of calcium and 2 moles of a chloride per solution. So why 1 and 2? Well, if we have, remember, when this guy breaks up, it's just 1 mole, right, of calcium. And because there are 2 chloride anions, it's going to be 2 Cl, right? So all you have to do is think about the fact that if it's a 1 molar solution, and I want to know what is the molarity, how many moles of, here, I'll write it better, actually. I'm gonna zoom in really fast so you can see. So again, we know that CaCl2 dissociates to form Ca2+, and then 2 chloride anions in water. Okay, so if we have a 1 molar CaCl2 solution, that means there's 1 mole of CaCl2 per 1 liter solution. Okay. It also means that within this 1 mole of calcium chloride, that represents, or that means that there's 1 mole of calcium 2 plus ions and 2 moles of chloride anions, okay, per 1 liter of that solution. All right, so there are several different things that you can look at here. If I ask you how many moles of the chloride anion is present in this situation right here, you would say 2 moles. If I asked you how many moles of calcium cation is present in a 1 molar solution of calcium chloride, you would say 1 mole. Okay. If I asked you how many moles of, calcium chloride is present in in this situation, you would say 1 mole of calcium chloride. But again, it's really what you do is the molarity of the ionic compound. When we reflect the molarity of the individual ions, we just look at the how many subscripts there are, how many of that respective ion are in that compound. So let me take this really fast. I'm just gonna bear with me. So, determine the molar concentration of sodium cation and phosphate anion in a 1 molar Na3PO4 solution. So, again, 1.50 molar Na3PO4 solution. All right. So, this means that for every 1.50 moles of Na3PO4, right, so you're going to take, there's only one, right? Oh, not one, I'm sorry, we'll do the phosphate one first. There's only 1 phosphate in here, so that means it's going to be 1.50 moles phosphate, right? And for 1.5, again, oops. And I just want to make sure that you understand Na3PO4 dissociates in water to make 3 sodium cations and 1 phosphate anion. Okay, so if we want to know the concentration of sodium cations, we're going to have to take this amount, 1.50, and multiply it, right, by 3. So that's going to be 4.50, get rid of that, mole Na plus. Okay, and again, I multiplied this by 3 because there are 3 sodium cations. So again, here is everything for you. So the formula unit of sodium phosphate contains 3 sodium cations. So the concentration of sodium cations is 3 times the concentration because there are 3 sodium cations per 1 formula unit of sodium phosphate. Since the same formula unit contains one phosphate ion, the concentration of phosphate is equal to the concentration of Na3PO4. Let's do another one. Determine the molar concentration of calcium and chloride in 0.75 molars of calcium chloride solution. So this is pretty straightforward and the same thing. So just remember calcium chloride, again, dissociates into Ca2 plus and 2 chloride anions. So if the concentration of this calcium chloride solution is 0.75 molar, then the concentration, then that's going to equal the concentration, because it's 1, the concentration of calcium 2 plus is going to be 0.75 molar in the same solution, and the concentration of chloride is going to equal, because there are 2 chloride anions, it's going to equal 2 times 0.75 molar. So it's going to be 1.50 molar Cl. Okay, pretty straightforward. All right, so now we're going to talk about dilutions really fast. So we talk about concentration. We talked about concentration. Now we're going to talk about how we can dilute something. So this is an example. This is a really good equation that you guys are going to use a lot. M1V1 equals M2V2. All right. So where M1 and V1 are the molarity and volume of the initial concentration. Right. That's why it's M subscript 1. And M2, V2 are the molarity and volume of the final concentration. Okay, the diluted concentration. So if you know this, and you know this, and you know this, you can figure that out. So essentially it's going to be algebra when we figure all these things out. So again, we're starting off with initial concentration at a certain volume, okay? And if we dilute it to a new volume, we're going to have a new concentration. That's essentially what it's saying, okay? And so we're going to use this a lot. The only time that people have problems with this this formula is identifying what's M1, V1, and M2, and what's V2, okay? And so we'll just go through it. So what is the molarity of a solution when 75 milliliters of a 4.00 molar KCl solution is diluted to a volume of 5.00 milliliters? So again, I'm going to go ahead and I'm going to make my M1 V1 in purple. I'm going to make my M2 V2 in blue. And I'm going to make sure that you understand where the variables fall. Okay, so what is the molarity of a solution when 75 milliliters of a 4.00 molar KCl solution is diluted to a volume of 500 ml? Okay, so our V2 is 500 ml. Our M2, we don't know, okay, because it says what is the molarity of essentially the new solution. And then finally our V1 is going to be 75 milliliters. And our M1 is going to be 4.00 molar. Okay, so if we take this and we arrange to solve for M1, it's going to be, and I'm going to actually write it up here, it's going to be, and I'll do this all, or we're going to solve for, M2, we're going to solve for M2, it's going to be M2 is going to equal V2 over M1 V1. All right, so now I'm going to take that and I'm going to plug that in down here. M1 is going to be 4.00 molar, put that in parentheses, okay. V1 is going to be 75 0.0 milliliter. And that's going to go over V2, which is 5, oops. Okay, again, that's going to equal M2. Now here's the thing, this is a dilution, right? We diluted 75 milliliters. We took 75 milliliters of this molar solution, 4 molar KCl aqueous solution, and diluted it to a volume of 500, okay? Now, if the volumes, so obviously the molarities have to be in molarity, right? Moles per liter. But if the volumes that you're working with, are in the same unit as they are here, milliliter and milliliter, you don't have to convert to liter. You can, because those will just cancel directly out, okay? So keep that in mind. It's okay to keep it in liter. So again, before we do anything, you can see milliliters cancel, and our answer is left in molar, which is what we want. So we're going to take 4.00 multiplied by 75.0 over 500, and that's going to give us, I just want to make sure my order, let me just do one thing real fast, my calculator, 4.00 multiplied by 75.0 over 500, and that's going to give us, so a new molarity, so M2 is going to equal 0.600 M. Okay. Again, because we took all this, we isolated the variables, we figured out which one we needed to solve for, which was M2, and then we rearranged it and rearranged for M2, plugged in our numbers, made sure that our units cancel, and they did correctly. Okay, so this is another, this is for, I went through it with you, but here you can go through it all yourself too and read through it and take a look. Okay, here's another example. Prepare 5.00 liters of 150 molar KCl solution from a 12 molar stock solution of the same. Okay, so again, we have to take a 12 molar stock solution and we have to essentially prepare 5 liters of 150 milliliter, 5 liters with a new concentration of 1.5 molar. So how are we going to isolate, how are we going to make sure we understand these variables? Remember M1, V1, M2, V2. So what we have to do, you're going to have to make sure that you understand which one's what. So you're going to prepare 5 liters of a 1.5 molar KCl solution from a 12.0 molar stock solution. All right. So M1, our original concentration, we're starting off with 12.00 molar. Okay. We need to end with 1.50 molar. That's our target concentration. And what we need to do is we have to, so V2 is going to be this right here because that's our target, that's our end amount, right? That's how much we want, essentially 5 liters of a solution that is 1.50 molar concentration. So 5.00 liters. So the question is, how much, the question is, how much of this solution do we need to make 5 liters and have a concentration of 1.50 molar? So we're going to have to take a certain amount of this solution and dilute it to 5 liters, and we want our target molarity to be 1.50 molar. All right, so we're solving for V1. So I'm going to actually do this. So remember, again, M1 V1 equals M2 V2. All right, we're going to rearrange and solve for V1. So that means that V1 is equal to M2 V2 over M1. Right? So now I'm going to take M2, which is 5.00 liters, multiply that by, oh sorry, that's V2. It's okay, multiply it by, well here, I don't want to confuse anybody. M2, 1.50 molar, multiply that by 5.00 liters, and that's going to go over our M1, which is 12.0 molar solution. And that's going to give us 1.50 multiplied by 5.00 over 12.0. So that's going to give us 0.625, and our answer is going to be in liter. Okay, and again, you can see that because our units cancel, so our answer has to be in liter, right? So 0.625 liters. So 0.625 liters of this concentrated solution, and if we dilute 0.625 of this solution to 5 liters, we'll have a new concentration of 1.50 molar. Fun stuff. All right, I'm going to stop here. We'll talk about stoichiometry in just a second, but I wanna get this going. This is going to be a really short lecture at the very end, okay? But I will stop here and we'll pick up on stoichiometry. Oh, I have to turn off my guidance, sorry.